All right, so my talk is going to be about measure theory and how it's used to construct a formal theory of probability, which is eventually how we prove Bayes' theorem and any other probability theorem we care about. So measure theory is a branch of math where we're asking questions about areas, lengths, volumes, and anything else we consider a measure. So probability is actually considered a measure, and it's because it is similar to area, length, and volume in that it's about assigning a value to a subset of a space. So for length, we care about take a subset of points on a line, and we want to assign a number to that subset that corresponds to a length. For an interval, we know how to do that. In probability, we care about the same sort of questions, but the space is the sample space, and the subset we call an event. So for two dice that are being rolled, we might have a sample space, say, be a set of ordered pairs with entries 1 through 6. An event like rolling doubles would be when the ordered pair is like 1, 1 or 2, 2 or anything like that. We have a way of assigning probability to that. We generally can do that pretty well for a lot of things like that correspond to real world events. We can define continuous probability distributions, and then we're thinking in areas and volumes, but we're still able to assign measures to most things that we care about. But if we start to ask sort of more difficult questions about what we can and can't assign probabilities to, we end up thinking about strange subsets of the real line, like one being visualized here, that actually, some of which it's really hard to figure out how you would assign probability to them or length to them, and some of which we can actually prove that it's impossible to assign such a value to certain subsets. And so the talk is just going to be about how we know these things to be true, and eventually using the formal definitions of measure theory to